Polly, want a cracker? Polly, want a cracker? More like Polly, want a nomial, because today we enter Unit 7, and with it, the exciting world of polynomials. Last unit, we learned all these rules for simplifying exponents and square roots and cube roots, but why do we care about the laws of exponents and properties of radicals anyway? What do they do for us? Well, as it turns out, they are the foundation for working with polynomials, these things that are going to follow us for the rest of our time in Algebra 1 and beyond. Today, our goal in Class 1 of Unit 7 is learning how we add and subtract them. But first, we need a little bit of terminology, courtesy of the ghosts of mathematicians past, to make sure that we're on the same page. If I want to know what a polynomial is, I first need to know what a monomial is. Now, maybe you know a little bit of Latin. What does the prefix mono usually indicate? Why do you think I'm calling these monomials? 5, 4, 3, 2, 1, and stop. Well, hopefully you know the word mono usually indicates one. In this case, we've got one term. Either, if it's a monomial, it could just be a number, like -9. It could just be a variable, like x or z to the power of 7,000. Or it could be a combination of numbers and variables connected by multiplication. In other words, we call them a product. So, given a monomial, by the way, notice, what are the things that you don't see? What operations would not meet this definition? Go. 5, 4, 3, 2, 1. Well, we don't see any addition or subtraction. Even though, for example, that fifth one there is negative, it's not being added or subtracted to anything. If it's a monomial, we will never see any pluses or minuses. Only one term. Given monomials, mathematicians love to compare them, and the way that we compare them is by labeling their degree. It tells us something about their size or their influence or their power. The degree of a monomial is determined by counting its exponents, but specifically, we are only interested in counting the exponents on the variables. So taking each of these 6 monomials here, I want you to take 30 seconds, pause the video. Let's find their degrees by counting up the exponents on the variables. Go ahead. And stop. So for something like -9, I can only count up the powers of the variables. -9 doesn't have any variables to count up. So for any constant, in other words, just a number, whenever we don't see any variables, we say that the degree of that term will always be 0, right? I cannot count up any exponents. If you want to be really annoying about it, you could say that attached to any value without a variable is a variable to the power of 0, right? Which would just be times 1. So here, that invisible exponent of 0 gives this term a degree of 0. Same thing over here, 17 squared all the way on the right. Even though I see an exponent of 2, it is not attached to a variable. This is just a constant. Its degree is 0. But for z to the power of 7,000, well, I can count up an exponent on a variable there. The degree of this guy is just going to be 7,000. Same thing over here for x. Even though I can't see it, it does have an invisible exponent of 1. So I would say that this term has a degree of 1. For -3, c to the 24th, d to the power of 57. Again, to find the degree, I sum. In other words, I add up the powers on the variables. So the degree here should be 24 plus 57, which is 81. Same thing over here for 18, m to the 6th, n to the 0, p to the 7, q to the 13. Once again, to find the degree, I'm going to take the 6, 0, 7, and 13 exponents on my variables, add them up. Feel free to fact check me. This should give me a degree of 26. Fantastic. Now that we know how to find the degree of a monomial, and in fact what a monomial is, we have everything that we need to talk about polynomials. So where our monomials had no addition or subtraction, when we throw in plus and minus signs, we get our polynomials. We get a bunch of monomials that are connected to each other by addition and subtraction. Now, within this very broad definition, there are lots of different subtypes or classifications. Mathematicians love to classify, and we have two really common classifications that we'll see for polynomials that look like these. For 7v minus 4, this guy has two terms, two monomials connected by addition or subtraction. A prefix that you might know for two, just like a bicycle has two wheels, a binomial has two terms. For the one over on the right, x squared plus x minus 12, this guy has three terms, x squared, x, and 12. So here, just like a tricycle has three wheels, we'll call this a trinomial, which is a polynomial with three terms. Cool. Given a polynomial, just like a monomial, we can find its degree. But finding the degree of a polynomial is a little bit different. Just like in, all of our explanations past, if it ain't broke, don't fix it. We know how to find the degree of a monomial. It turns out that the degree of the monomials will set the degrees of the polynomials. Specifically, what I'm going to do is take each of my terms, find their degree, and then the biggest one ends up having the most influence on the polynomial, so we match that to the degree of the polynomial. For 7v minus 4, for example, the way that I would do that, well, 7v, v has an invisible exponent of 1, so the degree of this term is 1. 4, right, it has a degree of 0, just like any number. So that tells me that for this whole polynomial, its degree is going to be the biggest one that I see. So this is a first degree polynomial. Same thing with this trinomial over here to the right. X squared has an exponent of 2. X has an invisible exponent of 1, so its degree is 1. Negative 12, it's a constant. It has no variables. Its degree is 0. Again, I take the biggest degree that I see here. 2 is the largest number, so that tells me that this is a second degree polynomial. You've got two more down below. Tell me the degree of each of these polynomials. Go ahead. And stop. 2n squared, right? N has an exponent of 2, so the degree of my first term is 2. N, invisible exponent of 1, this term has a degree of 1. 4, once again, no variables, has a degree of 0. M to the invisible power of 1, this guy has a degree of 1. N cubed would have a degree of 3. I take the largest one that I see, so the degree of this polynomial is 3. This would be a third degree polynomial. A cubed, b cubed, I would take 3 plus 3, the degree here is 6. 6ab to the fourth, a to the invisible power of 1. 1 plus 4 gives me a degree of 5 for this term. 2a cubed b, right, b to the invisible power of 1. 3 plus 1 gets me 4. And 4a squared b squared, 2 plus 2, the degree here is 4. I take the largest one that I see, so the degree of this polynomial is 6. Fantastic. Now, given a polynomial, it can have lots of terms, which means that there are lots of ways that we could order those terms. For consistency's sake, mathematicians often choose to write them in a particular order called the standard form of a polynomial. What do you think are the two criteria that are going to determine how we order our terms, given the possibly infinite permutations that we might go for? What do you think is going to determine the order? Go ahead. Five, four, three, two, one, and stop. Well, because we've been talking about degree, it probably has something to do with degrees. First of all, my primary criteria, my leading criteria, the polynomial terms with the largest degree, we will see have the biggest impact on the value of the polynomial. So we put the ones that have the most impact, in other words, the biggest degree, towards the front. So by convention, we will usually want to order our polynomial in terms of decreasing degrees. So I'm going to put the biggest degree terms at the front and the smallest degree terms at the back. My secondary criteria, after I've ordered them by degree, Just like we've done in the past, usually because I'm working with variables, I often want to put them after the fact in alphabetical order. Try it out with these guys below. Let's see if we can figure out the standard form for each of these three polynomials. First criteria, put the biggest degrees at the front, the smallest degrees at the back. If I need a tiebreaker, then I'll look to my alphabetical order. Go ahead. Come back, let's do it. So I've got, once again, this guy we actually did above. So 2n squared had a degree of 2, n had a degree of 1, 4 had a degree of 0, negative 2m has a degree of 1, n cubed has a degree of 3. To write it in standard form, sometimes abbreviated SF or San Francisco, I'm going to take the biggest degree terms and put them at the front. So n cubed is my biggest degree. That guy's going to go first, followed by the next biggest I see is a 2. So I'd put 2n squared next. Then between n and negative 2m, here's my tiebreaker. M comes before n in the alphabet, so negative 2m would come before positive n, and then we'll bring up the rear with our positive 4. For number 2, once again, we did this guy above, so I'll write 6, this guy was 5, this guy was 4, and this guy was 4 as my degrees. As it turns out here, this guy is already in standard form. The 6 is at the front, followed by the 5. And for the two 4s, you'll notice a cubed has a bigger exponent than a squared, so the a cubed term, even though it has the same degree, would come before the a squared term. And last but not least, 10xy to the third, x to the invisible power of 1, so this term has a degree of 4. 4y to the fourth, this guy also has a degree of 4. X squared, y squared, this guy once again has a degree of 4. So for my standard form, I'm now once again going to look at my alphabetical order as my tiebreaker. Notice here, x comes before y in the alphabet. Of my two terms with x's, I have one with an x to the first and one with an x squared. So the one with the x squared should come first. So this would be negative 5 x squared y squared, followed by my 10xy to the third, and then at the end would be my term with just y's. So there's our standard form. And in standard form, we may also be asked to identify the leading coefficient of a polynomial. Well, leading usually just means at the front, and coefficient, of course, that's just the number attached to our variable. So we say that the leading coefficient in standard form, this guy is just going to be the coefficient at the front. So let's take a couple of seconds. Let's find the leading coefficient of each of my three polynomials above. Go ahead. And stop. So n cubed, invisible coefficient of 1. This tells me that the leading coefficient, sometimes abbreviated as LC, is 1. Same thing for number 2. That term at the front also has an invisible times 1, so its leading coefficient is also going to be 1. And for number 3, at the front I see a negative 5x squared y squared, so the leading coefficient of this polynomial is negative 5. Cool! With all of this common vocabulary in mind, we now want to think about operations with polynomials. In other words, how we go about putting them together. Well, we'll start simple by doing some addition and subtraction. And while you might not have realized it, you've actually been adding and subtracting polynomials this whole time. If I give you two problems like this, what is it that I'm really asking you to do here? 5 seconds, go. 4 seconds, go. 3 seconds, go. 2 seconds, go. 1 second, go. Well, all I'm trying to do here is combine some like terms. It turns out that like terms, combining like terms, is all we're doing when we're working with adding and subtracting polynomials. Take 2 seconds, pause the video. By 2 seconds, I really mean more like a minute. Let's find the simplest form of each of these two polynomial expressions. Go ahead. Okay. For my first one, 11z plus 4z minus 9z. All I need to do is add my coefficients. Well, I've got 11 plus 4, so that gives me 15z. If I subtract 9z from that, 15 minus 9 gives me 6 z's in total. Same thing over here for my v's and u's. Well, the first thing that I might want to do is a little bit of distributive property. So in both of these sets of parentheses, I'm going to distribute first my coefficient of 6 and later my coefficient of invisible, -1. After doing my distributive property, this becomes v plus 6u minus 12 minus u. Distribute my negative sign, this becomes -3 plus 4v. All I've got to do now is find some like terms. Well, I've got v's that I can put together, I've got u's that I can put together, and I've got some numbers that I can combine. Well, v plus 4v gives me 5v. 6u minus u gives me 5u. And -12 minus 3, that gives me -15. Lovely. So what we know about combining like terms, not only is it a nice review, but it also tees us up really nicely for some of the questions about polynomials that we'll want answers to. At the top of that list, all of the terms here were linear. Their exponents were all 1. But monomials do not necessarily need to meet that criteria. So how would I know when any two monomials, even if their exponents are not 1, are combinable? Well, what do you think they need to have in common if I'm going to be able to put them together? In other words, for them to be like terms, or what we'll call like monomials. 30 seconds. What do you think are the two criteria they'll need to meet to be added or subtracted? Go. Alrighty. Well, as you've noticed above, I've got x squareds and x's. So first of all, they'll probably need to have the same variables. Just like our like terms above, I can only put u's together and v's together. I can only put x's together and y's together. But not only will they need the same variables, but notice an x squared and an x are different flavors of x. I can't combine them because they don't have the same exponents. So our two criteria, if they are combinable, not only do they have the same variables, but all of those variables need to be raised to the same exponents. In these 4 examples below, I want you to tell me, are they going to be combinable? In other words, do they have all the same exponents, and do all those exponents, or not exponents, same variables, and do all of those variables have the same exponents? Go ahead. And stop. For number 1, I've got a squared m cubed, and I've got a -3a squared m cubed. Both of them have an a squared and an m cubed. These are like monomials. For number 2, I've got h to the 6th and p to the 2nd, h to the 2nd and p to the 6th. Even though the exponents are the same, notice that they are on swapped variables. These are not like terms. For 3, again, both of them have e's and g's, but notice that this e has a power of 3, whereas the e in the second term has an invisible power of 1. These guys are not going to be combinable. Whereas for number 4, both of them have j to the 5th, both of them have k to the 4th, both of them have l. These are combinable. So with this idea in mind, if I look at something like 5x squared minus 3x minus 2 plus x squared minus 2x minus 7, as long as I can identify some like terms, all I need to do is put those terms together just as I would my like terms above. Take 30 seconds and pause the video. What do you think the fully simplified form of this expression here is going to be, knowing that my goal is just to put my like terms together? Go ahead. Alrighty. Well, I can't put x squared with x, but I can put two x squareds together. I've got 5x squareds and I add an x squared, that would give me 6x squareds in total. I've got negative 3x minus 2x. Well, that's just negative 5x. And then I've got negative 2 minus 7, 6x squared minus 5x minus 9 is my final answer.